Hello and welcome. While we wait for more participants to flow onto the platform, on screen is the ERIS content disclaimer. This webinar is being recorded and it will be posted on the ERIS website in the next few days. That's at erisinfo.com. Today's presentation will be about 1 hour in length. There will be time dedicated to Q&A after the formal presentation. So please enter any questions you have in the Q&A section of the platform. That's a separate section of the platform than the chat section. So the Q&A will be monitored and the chat section will not. So if you have a question you want answered, put it in the Q&A, please. All right, it's time to get started. I am Melanie Veltman. I'm the Director of Research and Data here at ERIS. ERIS, as you know, is an environmental risk data and information services company providing high-quality reports for environmental site assessors, conducting due diligence and site assessments of real property. ERIS uses the most advanced platforms and tools to help environmental professionals review and analyze critical environmental data records and historical products. Our latest platform, Scriva, brings ERIS project information about your site seamlessly into the report writing phase. And this can all start during your on-site visit with our ERIS mobile app. But we're here today for the webinar. So today's webinar focuses on background threshold values that represent the concentrations of hazardous substances used as defensible reference points to determine whether a release has occurred and why knowing these background threshold values, BTVs, is important to the risk assessment process. We're very fortunate to have with us today Dr. Kenneth Tramm, the Principal of Modern Geosciences. Dr. Tramm has more than 25 years of experience working on environmental assessment and remediation projects across the US. So now's the time. Without further ado, I'll turn it over to you, Kenneth, to tell us the why and how of background threshold values.
Okay, thank you. Can you hear me all right? Just to double check before we go. And how's my pointer on the screen?
The laser pointer?
My laser pointer, is it pointing?
Yes, it is. It's glowing and pointing and you sound great.
All right, then we're go for launch. All right, let me advance it down here. All right. All right, well, thank you very much, everybody, for coming, and thank you for that introduction, Melanie. A few things I just want to mention that I would like to get to. There's a lot packed into this presentation, and so that I can hopefully cover all the topics well enough. We can dive deeper perhaps into Q&A if that's necessary, but obviously a little bit of refresher on this term that is risk-based corrective action. It obviously means different things in different states perhaps, but usually is the cost-effective way to go forward to fix your problem. And then I want to actually put a scenario together so you guys can walk with me through why is the BTV important, and then we'll talk about some tools to get it, and we'll choose a state. In this case, I've just chosen Oklahoma to walk through that. There are two journals papers that came about from this research. One is kind of focused on the why, and that one's out, and the DOI is down below. And there'll be a QR code at the end if you are interested in that. And then the how is one that just hit the streets recently. And that's some of what we're really going to talk about today, because I want to pass on the how. All right, so if we're going to talk about risk at all, we have to give it a definition. Right, the most common accepted way to kind of describe risk as someone who's taught in this area for a long time is simply the toxicity times the exposure, or speaking now as I bring it into a regulatory context, I suppose, like cancer risk, right? So 1 person in 10,000, another additional incidence of cancer, 1 in 10,000 being a very high level of risk, and perhaps 1 in a million, 1 in a million being a lesser risk. So some regulatory standard typically will drive how we back calculate these values we'd leave in place. And they'll be driven by the toxicity of the compound, so chemical specific, and then the exposure, which has some different elements to it, right? The actual concentration you anticipate that would be at the point of exposure, and then all the assumptions that go into the modeling of what that exposure means. Within there, you have different routes: ingestion, dermal contact, groundwater ingestion, things like that. If I move that into risk-based corrective action, essentially, they're driven by the idea that you have a source, right? A release of some hazardous material. I've chosen that word specifically to be inclusive of more things than just hazardous substances, perhaps. A pathway, right? So we're going to inhale it, ingest it, perhaps we'll have dermal contact or another exposure pathway. And then we have some receptor assumed to be exposed. When these three are together, that's truly when you'll have your risk. Risk-based corrective action then recognizes these three principal players and looks at ways to mitigate or manage that risk. We can manage the pathway. We can manage the receptor, right? Putting limitations on what can be used at a piece of property, or we can actually address the source itself and decontaminate a property to reach some established goal. So if I take, right, so we've gone through risk-based corrective action. If we move that into kind of a more conceptual way to look at this, the EPA embraced holistically in the mid-90s this idea of risk-based corrective action, making some decisions about we want to see a decrease in some concentration of chemicals over time. So if we put effort in, so for example, on the x-axis, I've got some remedial processes happening, right? So we'd see a lowering of some concentration. And perhaps we'd have a risk goal that's then calculated by those things we just talked about. We have to be mindful of what a detection limit might be, right? So sometimes the detection limit may be higher than the goal. That's when we need better methods, right? So we're living through some of that in the PFAS generation now, right? That's all tempered against, okay, what's the cost of the different remedial options that we might choose? And obviously an optimum one would meet just this right here, the point where we would meet the risk goal in a decrease of the chemical concentrations, maximizing every dollar we spent to hit that goal. So what I'm going to talk about today is an added element to this, which is the fact that some of the compounds that we get involved in remediating exist in nature. So there will be a background concentration. So sometimes those existing background concentrations here before, and I don't mean anthropogenic in this case, but they could be. You could be in an environment where there's been impact by mankind that's affected everything. So urban areas often have PAHs, some elevated inorganics as well. You go to the Northwest, we may have orchard areas where we've got impacts from arsenic and other pesticides that have been applied. But I'm really speaking truly to an existing non-anthropogenic background for my discussion here. You can obviously move into anthropogenic if you want to. But that said, there's times when our risk goal is lower than that background number. It's also possible that we can never see down to what the existing concentration is for certain, let's say metals. I'm just going to pull it into metals, but it could be anything that exists naturally in nature. And so that's where we spend a lot of time screening and kind of get snagged into screening things in a little bit early. So that's a lot of what I'm going to talk about today. Now, for risk-based corrective action, which came about because we had a lot of things to fix and only so much money to do it, we want every dollar to count. We have two frameworks in the United States that we use for that. One is the EPA Soil Screening Guidance, came out in 1996. It is actually informed by things that came before it, such as the RAGS document, the Risk Assessment Guidance for Superfund, of which there are many, starting from 1989 on. They resulted in a generic risk-based soil screening levels, and the formulas and the assumptions that went into them actually inform most programs in the United States. Even if they are state-specific, they're still informed by these. Today, they've been expanded into what is accepted as the regional screening levels, and we'll talk about that in a second. But this is the original document from '96 that all my students have had to learn and memorize. The second part to the nuanced understanding of risk-based corrective action comes from ASTM. Right, so we had an emergency standard, which came out in '94 in response to really petroleum releases and the funds that fed into getting them addressed. That led into a petroleum-centric risk-based corrective action, one being finalized that lived from '95 to 2024, and it has passed now. we exclusively have the just chemical specific one that's lived on since 2000. That's it over there. But this gives you the terms such as tier 1, tier 2, tier 3 mindset. And that approach is incorporated into many state programs today. So these are your two frameworks in the universe of risk-based corrective action to be aware of. Both of them mention background. Now, it's hard when you're making a program that can be used anywhere, right? With ASTM, anywhere means anywhere. With EPA means United States, but to give you hard background numbers. So they both mention its importance, but leave it to other things to specify how to get there and to perform them. So it's good just to note that there's a placeholder in this world of risk-based corrective action for background. So knowing that, how we use background is important. So if I looked at a scale and I want to say which one's going to drive my risk program going forward, or maybe a screening level, let's say, right on one side, I've got risk criteria, which represents usually the lowest of all calculated values. So in this case, it could be something by a county, a state, or the EPA itself in those regional screening levels we talked about. And that'll be based on the risk criteria that's acceptable to them. Hence, that's the guy with the question mark next to him and a few of the things we've talked about before. And so that would be your driving risk criteria unless there is a background value, a defensible background value, right? So then this value would come in and become usually something that trumps that risk criteria. That's how most risk-based programs are established and set up to function. So I've now shrunk the whole universe of possible compounds we're going to talk about under the scenario of having a background to those that exist in nature, right? So I'm not talking about PERC or TCE or many of the PFAS compounds, although we could talk about anthropogenic background with some of those too. But the lowest of all your risk criteria or background. So with all that said, I wanted you to walk with me through a scenario, right? So you get to play consultant for a minute. Many of those on the call are and have done this exact scenario probably many times in their career. So let's say we were tasked, whatever led up to this, maybe it was a phase 1, maybe it was just somebody wanting to know this answer, but we were asked to actually go evaluate a piece of property, and we determined, hey, we need 5 samples to represent this small area we're looking at, and lead was our concern. That's right, so I'm going to take some samples, and if I was just interested in knowing what the lead concentration is, I'll obviously get my data back from the lab. In this case, my scenario here, I have a range from 22 to 27 milligrams per kilogram. So the real question is, knowing that, do I have a release or not? Right, so all right, let's look to what we would look at to know that. Now, you know some of that because we just talked about it, right? So I need to have some risk criteria. If I have none from my state, I can go pull the regional screening levels from the EPA. If my state has criteria, I could pull it from them. And the lowest of those risk criteria drives my risk unless there's a background value. So again, I'm talking lead, so we know lead exists naturally. So having this will be very important, especially when coupled with this. And then with those two together, I can actually get my screening value to then screen and say, do I have a release or not, right? So relatively simple. All right, so one thing to know about, if we looked at lead, and this is lead specific, right? So I mentioned that 1996 soil screening guidance document from EPA. If we went back in time a little bit, we could actually pull up and see the values that go with it. So if we've just highlighted lead here as I essentially have an ingestion-based number, an inhalation of particulate-based number, and then I have a soil to groundwater leaching number, right? So it will migrate from soil to groundwater, and then the number at groundwater would exceed something we would drink. Now, it's designed, the EPA framework, to have a dilution attenuation factor, don't go to sleep on me yet, right, of 20 if it is a half acre or less, or 1 if it is more than a half acre. So in this scenario, though, I'm sure you've by now looked down here and said, well, I see a lot of dashes, right? So what feeds into that is the fact that when EPA was putting together for the original compounds in the 90s, so 96 specifically, they noted, hey, we actually have guidance on this, and lead's not highly mobile and under typical soil conditions, so we're actually going to not put a number there. We want people to focus on this immediate risk number, ingestion-based, right, direct contact of 400. Now, earlier this year, hopefully some people have already said this to me, or at least are talking to their screen like I do, right, that, hey, that was updated to 200. 100 if you have two sources or more than one source. That is true. So today, if we looked at this, that number would be 200, right? So, okay, that's kind of the EPA federal level. Good to know that. If I actually went and Googled regional screening levels and I pull up the default table that Fred and his team at Oak Ridge National Laboratories has prepared for us. A shout out to Fred. Right, we can look there and we'll find that 200 that is current today. And we'd find that there is a groundwater number. Now there's not, if you looked here, right, there's not an RSL, or risk screening, regional screening level for risk-based numbers, but there is one that is based on the MCL. And it's only given for that assumption that's greater than a half acre. But nonetheless, that's where that number is. Now I mentioned that if you're less than a half acre, right, that would actually be a different number. So if we wanted to know that, the table doesn't give us that. So we've got to look under the hood. I've got to introduce a new idea to you, which is, okay, if I'm half acre or less, this partitioning coefficient plays a big role in understanding what that leaching is going to look like. So I've got to introduce that to you, but this is it right here. I won't force you to do the math, right? If we take our MCL and we plug it in, here's our KD. I'll keep it red just because it's important in its role. All right, there's some properties about water content in the soil, air content in the soil, bulk density of the soil. We run those through, it's 13.5. That's where this 14 comes from. And if we knew that we were half acre or less, we could do the next piece here, which is multiply it out to get our 270, right? So that 270 would be the number that would live still here if we had the less than a half acre. So we've now entered a fork in the road. Do I know that it's more than a half acre? Or is it less than a half acre? Well, I've got to carry both those numbers with me for the moment. That source size becomes real important in kind of making a release determination. It's easy if it's a chemical that we don't think is naturally occurring in nature, or we have a good history of a site and we can identify where the release is. That's easy. It's really these other scenarios where we're screening, perhaps the history has changed, and we're trying to make a decision over here. Maybe there was a historic point of a release that's affected here. This is the reason that we have to have a realistic and inclusive background number to make that decision. All right, let's get back into our scenario here. All right, so I've just pulled in the EPA regional screening levels here, right? We talked about that 14, that 270, and I'm going to refer to the other pathways together as human health. They're all human health, but I'm going to isolate groundwater protection from it for our scenario. But we've got our 200, and we've got our groundwater protection of 14 or 270, if I knew my source size. There's not a background number for lead from the EPA, a default one for you to use anywhere. So we're stuck with those to start from. So I've either got 14 or I've got 200, because you remember my scale, right? So 270 being higher than the 200, 200 wins. All right, so I've carried that one, so I can't totally answer that question yet. It's always good to look at other states and just different approaches. So if I went to Pennsylvania, the groundwater protection base number for lead is 450. The human health, again, being the other pathways, the lowest is 500. So from that, the number would be 450. If we were in Pennsylvania and we had a 22 to 27, we'd feel pretty good. I'll bring up Texas just because that's where I am right now. Our groundwater protection number in Texas is 3. And all these are in milligrams per kilogram, by the way. Human health is 500. We do get a background number in Texas, which is helpful, but it is a published median value, which means it's the 50th percentile of the entire state of data. So that could be problematic, and we'll talk about that in a second. But this would leave me with either the 3 or, on the other side of the scale, the 15. So 15 would be my driver here. To look at another state that approaches these things differently, just to give us context again, if we were in Hawaii, where they like to make fun of us mainlanders in our risk approach, they'll do batch testing to answer this question. They already used the human health value of 200. They had that in place before EPA changed their numbers, but they actually use what's called a background threshold value. Right? They did an independent study, looked at the data sets that came back and said, all right, let's calculate the high end of the curve of what is anticipated to be naturally occurring, and it's 73. So in that scenario, right, my lowest would be 73. So we'd screen out. So I've given you two ways to screen out. One is purely on the risk side, and one is driven by the background threshold value side, or a background number. And then we have Texas with these low numbers here. So just to emphasize where we are, right? So general EPA I could apply anywhere, Pennsylvania, Texas, and Hawaii. So one thing to note is how these numbers stack, and there's a decent range between them. So it's good to know the background to these pieces of the puzzle, so it can be helpful to you. So as we look at Texas, what I want to do is say, all right, well, what was the EPA default, right? So this is that soil screening level, calculated again, same numbers. If I plug that in and we just moved here to Texas, it's our soil to groundwater PCL, as we call it here, but the groundwater protection based number. We use a 10, where that 900 is the recommended KD value, right, for estimating the partitioning coefficient. If we apply our dilution attenuation factors, if we used a 1, it would be 0.15, but we get to use the 20 in Texas. We call it a lateral dilution factor here. That would get us the 3 that we use. As you look at the KD value for lead, sometimes it's helpful to give you things that are in context, right? So you're not very mobile once you get to a higher number of 50 or more of centimeters cubed per gram. But you'll be familiar with things. Here's one of my PFAS friends that we chase often, but BTEX, TCE, things that commonly in the soil we would anticipate would be highly mobile, and we should check groundwater. As we move up to less mobile species, you see we get different classifications. And so this is where the Texas KD value that we assume for our model would live, and this is where that 900 sits. Pennsylvania, just being different, likes to use 890. Almost everybody else likes to use that 900. There are some states that have done their own testing to demonstrate where that threshold is, and you'll find those are usually 10,000 plus. So lead is an interesting one because it occurs commonly. It's naturally occurring. Some places higher than others. It also has risk criteria to it that we are concerned about because it's just been part of our urban environment for a long time, and it has direct health implications. So it's just an interesting area we found ourselves in that we just need to know more about it and make some good decisions. Anyway, the assumptions that went into that 10, if you're interested, is the assumption that we have a 4.9 pH, which turns out to be very little of Texas. That is less than the value the EPA points to, and obviously less than most of the surface area. The second part is an assumption on the soil type, being sand versus what EPA recommends versus probably about 84 shows up in these 5 classes here. So the second part, so that was the risk part, right? Because that was my driver at 3, is that background part. And now this one's important because what we learn here can apply anywhere. So this is the original 81 data set, and these are the points from a USGS study, and that informed that median value. There is some very impressive data sets related to a 2013 study that a lot of states have started to use as their main reference point. It's up here in the right. If you're curious, just Google USGS data series 801. Worth a look. All the geospatial data is available to you. But we moved from having 119 samples in Texas to, I think roughly 1,200 or so 1,237. And the QA/QC component to this, of course, is very impressive as well because they specifically stay away from major highways, rural roads, buildings, and industrial activities. So an intent to be non-anthropogenic, but to be as natural as we can get, because we keep building out, we keep affecting our environment. If you wanted to see these two data sets collectively, the original 81 data set unfortunately had very limited detection. So you were either 30, 20, 15, 10, and this is half of the 10. I've just added it here to finish out my histogram. And this is where your 3 would sit there. This is the 2013 USGS data shown in a histogram, right? So this is frequency of occurrence, number of samples that meet this criteria. And then these are the actual concentrations. And I have actually the 5 centimeter horizon or interval, and then the A horizon and the C horizon with good equal distribution amongst those. But you'll quickly look, if you said we chose the median, which by its name, you knew we were probably going to penalize half the state, right? So there's this tail that we would expect to exist that we're going to miss in that. So that can be problematic. One thing when we were doing this research was to reach out to municipalities, and the reason for that is those municipalities always are where they are, right? So if you happen to be in that upper 50%, you're going to feel it more than maybe others would. And so some people don't pay attention to things until they see it cost them money. So we sent some surveys out to a few of the cities that are here in Texas and got their annual cost of demonstrating background again and again, or unfortunately, sometimes making remedial decisions based on that median value, because we can't use the 3. So we go to the 15. And then that policy has been in place for 20 years. And so you get to millions of dollars over just these 6 cities, right? It's not to emphasize this, but others just to say it's impactful, right? So seeing this led us to, okay, what are some options, right? Is there a better way to represent background? So the answer is yes. Let's go back to the original intent and the calling and the directions of like, what are we supposed to do with the way that we sample and our protocols? So if we go back to 92, and this really pulls, of course, I'm an Aggie from A&M, so there's probably some hissing out there at that moment. But one of the A&M professors is actually quoted in an EPA document, and it's pretty rare for me to see them to call out somebody's quote for direction. But in this case, emphasizing when this began I mean, how do we assess properties, and how do we assess, in this case, soil specifically? So spatial variability is not an academic question, right? It exists whether we want to argue about it or not. What we need to understand is the magnitude of that, and understand that we can't put a single value to it unless that single value is inclusive, or more specifically, we accommodate the existence of that variability in whatever models we use. So as a driving force or a directive, that informed the way EPA put together a lot of its background thinking. So ITRC did some fantastic work in 2021, 2022, just on the development of background threshold values. If you're not familiar with it, I highly recommend you pull some of those up. A lot of work and thoughtful process from many, many states went into that. Really, how do we arrive at this number for screening purposes that allows us to do exactly what we try to do in my scenario here? Meanwhile, EPA improved its tools, right? So anyone not familiar with Pro UCL, that's your next thing to write down and Google. It's freeware paid by your tax dollars. And it's a fantastic tool to allow you to touch and evaluate and review your data sets. So from the EPA, though, we definitely know the sources of data that we can get includes the USGS data or more localized information when available. But we want to represent the upper threshold of an expected population. So that just means I'm going to pull you into statistics for a minute. So hang with me. We need some tools, right? So just about everybody has worked very hard to purge their statistical learning that they did in school, and I don't blame you. But it's coming back, and it turns out these are very helpful just to understand as we live in the age of big data, right? So the mean itself, obviously self-explanatory, arithmetic average most often. The median, we've already spoken about, the 50th percentile. The mode's a harder one when we look at data sets with limited resolution. As you get more resolution, it's hard to get to your mode, but limited resolution, we may find this to be a poor statistical term. But the standard deviation you should be familiar with, and the coefficient of variance, which is simply your standard deviation divided by your mean. Very helpful to anyone familiar with statistics will know this is what most programs point to first to say, hey, is your data normal enough to make some decisions? I'm going to add to that the relative percent difference between the mean and the median, only because I want to see how those two come together. All right, so those are tools, or maybe more factors. True tools would be these. Hopefully you, the crowd listening to this, is familiar with the 95% UCL, and I mean the 95% when I talk about any of these, but the UCL, the UPL, the UTL, and the USL. right? So these are in order of conservative, most conservative at the top, least conservative at the bottom, right? So I'll obviously have to have a very impressive data set to even propose a USL. The most common background threshold value tool is probably the 95% UTL, and a conservative one, less realistic, but used, is the UPL. But those are the three that I want to talk about. But first, I can't start statistics without showing you a curve, right? So hopefully you remember from school that within a Gaussian distribution, and there's Carl, you can look at him if you're tired of looking at me, right within one standard deviation each way from the mean, we should have 68% of our population in a theoretical perfect world of a Gaussian distribution. Within 2 standard deviations, we'll have 95%, and then within 3, which not drawn on here, would be 99.7. So now what I have to do when we're doing background concentration, so something that has a non-negative number, is do a one-tailed evaluation. So if I was going to take that away and give you a one-tail, right, this is actually where about your 95th percentile sits if it was perfect. Obviously, it's never perfect where the mean, median, and the mode are all the same number, but we try to get as close as we can so we can make determinations from that, or we use more elaborate statistical approaches. Right, so I'm just going to draw these out. This is where the mean is, 1 standard deviation, 2, and then 3 would sit somewhere about here. And now that we're doing a one-tail, you see that my inclusiveness in the population has changed a little bit, but that's how it looks with a one-tail test. All right, so let's see where those tools that we just spoke about would sit, right? So the 95% UCL sits about here, UPL, UTL, and the USL, right? So the USL probably sits close to and just under that third standard deviation being added to the mean. And I say that having gone through enough data to see performatively, how do we see where these things sit as we play with normal distribution and normal data sets. So most conservative, probably least likely to represent any background. Then we head to these 3 tools right here, and those are the ones that we looked at in our research. All right, the only other thing I want to do is I want to leave the Gaussian distribution only because nothing's ever perfectly a Gaussian in distribution. Rather, the real world has things with tails, right? And your most common one for naturally occurring concentrations of, let's say, compounds or metals is going to be a right-tailed set. There's very few that are high, but they are high. And then there's going to be more mass or common occurrence within a central tendency will be within these 3 right here. One thing to note, so if I anticipate right-tailed data to be the most common that I will encounter in the natural environment, the median is always less than the mean, right? So shown over here, right? So this, and just looking at quartiles, I'm going to actually not represent the 50th or 50% of the likely concentrations. I'm actually penalizing the most common occurrence of data sets by choosing the median. Now, the median is a fine tool if I want to know what is least disturbed by tailed or skewness in data sets, but it is probably not the right choice because it's just overly conservative versus the mean in a naturally occurring data set. Now, left-tailed, you'll see it does the opposite. Less common that you would have this in natural data sets. In fact, I typically find this when I've over-censored data, right? When my other peers here are like, you've censored your data too much. So anyway, I just want to mention those specifics, and that's how the performance of the mean and the median are in normal right-tailed data sets. And so, right, you may remember before we got into the UPL, UTL, USL, I mentioned the relative percent between the median and the mean. As those become closer together, I know that the curve is starting to get more where it has equal sides, and it's more Gaussian in nature. So that becomes a tool that we look to in a second. All right, what data? Obviously, local data is always preferred in a background study. So if I have a site where I can get undisturbed samples and actually derive my own background values, that's preferred. In a scenario where I've just taken my 5 samples and I just want to say, is it here or not? That's probably not, it would cost more to do the second part than even the first part. But if I'm in a regulatory program, that may be something that's useful unless there is defensible data to work with. Moving from local data, we have state, and then maybe some other agency has signed off on or performed in a way that would be acceptable to a regulatory entity. And the third, and probably the most common used and referenced by EPA and others, is to use USGS data or something, again, that's collected maybe academically or NRCS or something similar to that. So I have up here this kind of 1975 vintage is what that map is from. It's from the Shacklet study that's probably referenced more often than not in your state guidance, at least if your state guidance is pre-2015 or so. And so that's limited in data set quality. You'll see, if you stare at it long enough, you'll start to see highways because it really informed where some of those points were collected. Nonetheless, decent data. Covered good compounds and spatially at least hit all the conterminous United States. There's more focused area data as you head to the NURA study, but that is not as rich in soil as it is in sediment. There's some NRCS studies that are helpful but limited in value only because look at the density. There's a second one done, it's the part of the National Geochemical Survey. Again, this is limited in soil content to specific areas, but it was meant to kind of patch. You see some patchiness where we're filling in data sets there. And then there's another NRCS one that was done more recently, but that 2013 one that I referenced, this is what that looked like. And this is why people have turned to it, because they improved both their methodology, so they have representation on a good spatial coverage, but their quality control was about as good as I've ever seen in any of these USGS studies and many EPA studies. So it gave us something to start with. So if I was going to start with something, I would begin there. All right, so we've mentioned the UPL, we've mentioned the UTL, we've mentioned the USL. So now, why would I choose one over the other, right? So this is the effort that was done in our second of those two paper, right? So I had the why, and this is the how. So what we did is we calibrated some decision points based on its performance of normality, defensibility when we did visual review of data sets to determine when is it more likely than not that we have no outliers, a hard ask, or we perform so normally in our distribution that the UTL makes sense, or it's acceptable, but it's not great. So in that case, if I just put these together, right, the most conservative being the UPL, the most inclusive being the USL, we have a minimum sample set size, and then we have some requirements for our correlation coefficient, and then our CV, coefficient of variance, right? So this right here, this criteria, only the CV is typically the threshold required by most states and by the EPA. So really everybody's in at this number. We've just added more conservative criteria to it as we've made some decisions about censoring. And so they're based on the CV, the R, and that relative percent difference between the mean and the median. So it'll make more sense if we actually like put it to use. Right? So for example, I told you we'd look at Oklahoma. So welcome to Oklahoma, a friendly state. If we looked at lead concentrations in that 2013 USGS data, right? So just go with me on this column right here, right? If I did no censoring whatsoever, I have a sample set of 333 samples. The minimum is 5.3 parts per million, or milligrams per kilogram. The maximum is 122. Here's your mean, here's your median, right? So from this, you already see that our mean is, like, you already can feel the right tail, right? You can feel it already. The relative percent difference is a little bit high because we're shooting for 10% before we'd ever think about a USL being on the table. Here's our standard deviation, our CV, and our R. So in this case, my CV actually is well below the 1, right? So typical fashion, if I just used EPA guidance on making a decision of putting a UTL together, that would satisfy and we could grab it, which would be down here at 35. Now we've added the R, which we'll talk about in a second. I really haven't given you much data on that. And then each of the other columns is where I'm censoring only the right tail, right? So I'm chopping off at 100. Nobody in here is above 100 ppm, 50, 45, 30, to see how the performance changed, right? So over here on the right is kind of my steps to that. Obviously, find your data, then process it through Pro-UCL. I'll show you what that looks like in a second, and then start doing your censoring to see if this data set presents as having an outlier. So looking at your data, evaluating it under different scenarios, there's nothing better than that. So if I put this data together, now I didn't give you each of the concentrations because that would be too long for this page, but if we ran it through, you can see that's where I got my 333 from, my maximum, my mean, my median, my coefficient of variance, and then I've got my 3 possible estimators, right? So we ran it through here, and we're going to make the assumption that everything's behaving with a normal distribution. Now, it certainly is worthwhile looking at any data set to say, hey, this is log normal, this is non-parametric, and Pro-UCL can do those things too. What I'm doing in this process is making a conservative approach that would have increased likelihood of regulator acceptance, right? Let's stay conservative and stay more conservative than the EPA has put forward for our purposes. So with that said, I'll remove that. All right, so let's talk about how I got that R, right? So that, again, in Pro-UCL, but for those not familiar with QQ plots, these are QQ plots right here. Next to them, right, so there I'm gonna point to those, are these frequency histograms, right? So part of my reason to show you the lead ones for Texas was I wanted you to see what they look like. So this is about as Gaussian, you know, it's a little bit blocky here. We get more heavy-tailed here. We get right-tailed here, and we get a little bit left-tailed there. So the correlating QQ plots, right? So I'm looking for the rise over run, essentially, of each of these to have an understanding of our correlation. So this is the one that's probably the most common one you'll see, the right-skewed data set. And if you'll notice, it makes a little bit of a smiley face here. So from that, we can get the R value, and this will be calculated for you specifically so you can make your own. They're usually done in 6 quantiles, right? So I'll have concentrations over here, and I'll have quantiles of occurrence on the x-axis. So this is what they look like straight out of Pro-UCL. So for example, I'm going to use our Texas one where we used lead, and I used the 1237 or so that are in the state, put them all together, and this is what it came out as. So from this, you can make the decision probably visually. It looks like we've got some decent gaps here. Let's go ahead and call those outliers. You know, on my team, as well as when we deal with even with some regulators, they're like, well, it's probably not outliers. It's part of a heavy tail. It's totally true. But for our purposes of just censoring so we can get the most inclusive estimator, we'll want to remove those. And this is what that looks like when you do it. And you can see my smile kind of forming there. So in this case, this original data set, I had a CV of less than 1. So if I just was using the blanket requirements from EPA, it would meet numerically. But the R that we've proposed, our correlation coefficient here was 0.657. So it didn't meet my 7 requirement. As soon as we censored it, you can see I've dropped my CV down even further to 0.4, which is very good. And then my R has improved. It's not quite 1, but for a data set like this is pretty impressive. So this then would allow the use of the USL from this data set. And if you're curious about kind of EPA's opinion on outliers, if you Googled, a lot of Googling requests from me today. Lead background EPA, you'll find in their website lists for different states. And if you clicked on Texas, you'll see the full data set, and they've actually chosen to censor it at 41 as well. So this is actually theirs. This is their QQ plot that they present. Anyway, that's about censoring so I could get my highest R value to work with. All right, back to Oklahoma. Everybody still with me? Good. Right, so this right here I've taken in Pro-UCL, and I've just taken the data sets that we all went through, right? So that 333, no censoring one, until I censored it at 100, I censored at 50, I censored at 45, and I censored at 30. And it's just giving me the data output for each of those, but they're all on top. I'm gonna put in the corner over here, each one by itself, but essentially, right, the CV was good enough, the R was good enough. I could choose a UPL of 34.05 from that original data set. it met criteria, and it looked like this by itself. Not horrible, but a decent gap. So if we actually censored it at 100, you can see I now get improved performance, and I become decent enough, right, to meet my threshold criteria to allow a UTL, right? That would be a 29.17. If we censor again at 50, I get a minimal improvement. If we censor again at 45, still minimal improvement. And if we censor again at 30, we get a very tight data set that now would allow the use of a USL, right? It now meets our CV, our R, and our relative percent difference between the mean and the median, right? So what we're doing is trying to make some choices of normality performance goals, right? That's our term, not catchy, I know, but we're not creative in that way. This is the most inclusive, this is the most conservative choice of an estimator. Now, I'll pull you back into Texas just for a second. There's another way to use these two. Once you have different variables to play off of each other, you're probably familiar with a quadrant graph. This is a normality quadrant graph where we simply took data from USGS and we ran it through different ecoregions of Texas, right? I didn't define these regions. These come from the TCEQ themselves. So we just ran it through GIS, popped out the data sets and said, how did lead perform, right? So within the range for the use of a UPL, 2 of them fell without any censoring. We just ran it through. I think one more, the Central Plains, which is number 3, so over here. And then several of them fit in the USL just by themselves. So having data that performs so normally is pretty impressive. And this also is a helpful tool if you need to censor your data and see it visually. So this was done just lead in different regions. So if I take this, go back to Oklahoma, and I'm doing the exact same data set where I took the full data set, this is where that sat. This is where I censored it at 100, at 50, at 45, and at 30, right? And this is just comparing the CV to the R from the QQ plot. All right, that's 2 ways to look at your data. My favorite way to look at your data and understand this is actually a histogram. I've already shown you those, but since we're talking Oklahoma, this is Oklahoma right off the bat, and I've got up in the right kind of our statistics that go with this. And so this is a pretty crude looking heavy right tail because I've got 2 points that are so small you don't see them over here, but it would allow the UPL in here, but it wouldn't allow a USL and it wouldn't allow a UTL. If we censor it one time, again at 100, you can see the immediate improvement, right? We have to our histogram. If we censor it a second time, we see improvement, but not enough. A third time at 45, and it takes again to that 30 before we now see a decent Gaussian-like distribution. And under that circumstance, we meet the USL goals to choose, because our median and mean are now close enough to choose a UPL, a UTL, or in this case, a USL. Now, going back to the full data set, which is a full data set presented here, right? Essentially, this is our population. And obviously would be inclusive of subpopulations, as you saw in that Texas example with different regions. This is where the UPL would have put it. So you can see it sits on the end of the right tail and likely is a reasonable estimator. That actually is more inclusive, a higher value, than what we got by censoring further. But you never know that until you go through the process. So if we took that same process and we applied it, because we did as part of our calibration of these choices for the United States, that brings us back to our scenario, right? So I've got my 22 to 27 lead. I'm still trying to answer that question. Does this look like I have a release? So, right, if you remember where we left our story, Pennsylvania, I knew I didn't have a problem just because I was below the risk criteria and it wouldn't drive anything. I actually now know that there's higher background values to be had there. Although if I was in Florida, less so. And maybe if I head to North Dakota, less so. So I wouldn't expect to see these concentrations there. A second compound that we did it for, or metalloid, really, as a soil scientist, I'm forced to say that. Right, this is arsenic. So just to give you an idea of using that same process, and you let the estimator that is the most inclusive but represents the individual data set, this is what you would come out with for those points. Doing some, anecdotal review of different states and things they've got to, most of this is not inconsistent. Most of it is consistent with kind of the background values most of the states use. Not Texas, different, longer story, working on that. So the only other thing I'd want to point out with the time I've got for a few seconds, because I want to leave some Q&A time, is doing this for regional work. Things to point out is that the USGS data sets and the analysis methods are slightly different than the EPA methods. So if you're doing it for risk purposes, you'll want to make sure that the end output is consistent with if I did it by an EPA method, right? So if I was going to run by 60-10, 60-20, 71-41 for mercury. Things we know from prior studies is essentially aluminum, extremely high. So I wouldn't choose anything higher than a UCL if I was going to use that data set. Barium, chromium, and vanadium, a little high. There definitely seems to be a bias. It's either based on the grain size choices or the acids for digestion. And likewise, mercury will be biased low. Obviously, putting it in an oven for a while is going to cook off some mercury. This is your data set that USGS put together. Thank you to Daniel Smith and his team and all his work. This is the 5 centimeter where he actually has it kind of color coordinated. So you can see where the arsenic has just some commonality in certain places and it's lower in certain places, right? This matches up with some of what I just showed you before. Each of those can be pulled in. This is actually in Google Earth. I just pulled it in so I could play with it. And you can see the individual concentrations by clicking through, and you can develop your own data set to work backwards from. I'll give you an example for Texas because that's where I'm sitting in right now. So I had done one for the Dallas-Fort Worth area, which really is the surrounding counties as well. Something to note is, there was in this large area that you see here, there was only 4 samples in that 1981 data set that had 119 across Texas, but there are 48 individual samples, so up to 3 per from across the area. So we have a higher resolution today, but if I were just to run through that same process that I just did for you, and we look at the performance of our CV by now, because you are all now statisticians, I feel like you've survived me throwing a lot of acronyms at you. I should send you all certificates. And the R values are pretty darn impressive too. I have 2 of those QQ plots that we ended up with here. The relative percent difference between, right, the median and the mean, right? If you look at these, really good performance, meaning they're coming together close enough that we actually will take on a normal distribution, even if we're not. That would lead you to a 19.5 and a 36 essentially. And I'll wave at you from where I am. So with that, I know I've thrown a whole bunch out there and there's a lot more to talk about, but I hope you enjoyed the journey. And I'll say thank you and ask if there's any questions. Hopefully I've left some time, Melanie.
Wow. Yeah, we do have a few moments. I'll just start by saying thank you, Kenneth. That felt like a semester's worth of information and very valuable, very thorough. So yeah, I'll get started with a few of the questions that came in. Certainly appreciate those questions coming from the audience. Hopefully one of them is quick. Kenneth, what software were those QQ plots and histograms generated with?
Sure. So Pro UCL, and right, so use your search engine of choice. I'll say Google more as a verb, but right, Pro UCL, I think they're on version 5.2 right now, and you'll find the EPA website. It's downloadable. Get the 2 documents that go with it on use and limitations. But a very useful tool, and it's very regulator accepted, right? It has, I'm a fan of R and SAS is what I learned in school, but Pro UCL does the things we need for this specific purpose and has regulatory acceptance. So it's, as I tell my students in school when we use it, it's more like a car wash, right? So you're going to roll up your windows, you're going to have everything prepared, and you'll roll on through, and it will do the rest of it for you.
Awesome. Thank you. So Kenneth, you had mentioned regulator acceptance, and we had a question that came in through the registrations that seems similar to that, I guess.
Okay.
How would the validity of the background threshold values be assessed or measured?
Well, I mean, that's part of it is obviously the data sets come in any data set. You need to define its entire provenance, right? So why were these sampled? Did they avoid sources? Like all those things I emphasize on that one slide. So that's your start. So whether you're collecting your own or you are using data sets collected by others, I'll say USGS because that's available to all of us. And when I went through that data set, Melanie, that same data set extends into Mexico and extends into Canada, right? So cooperation from all those governments exists. And so there's a larger data set. So the provenance of how it was collected is vital. The methodology in which it was analyzed to get your data and the quality control, vital. So I can speak to those two from USGS. Obviously, if you're developing your own program, match those. The last part is once you know the data represents what it's supposed to represent, was collected from where it was supposed to be collected, so spatially relevant, then is the analysis portion of it. And so what I've done in this second paper that we wrote is specifically focus on the analysis portion, right? So taking that data and looking at it defensively and conservatively so that a regulator should have acceptance. And I say that meaning we are bookended by being more conservative than the EPA allows us to use. And I've used in many other states in developing background work. I always erred towards the more conservative. So when you show up at the end of the day, you're not dealing with numbers that are drastically different. So that's a hard question to answer other than you have to go through that entire story and make sure you can defend your data.
Got it. That makes sense. Thank you, Kenneth. There's an attendee who has asked if you can just very briefly re-explain the concept of censoring, where you take some of those data points out because you might have to defend those choices as well, right?
Correct. And so in traditional censoring, so there's a lot of different treatments of data. So on the low end will be what is your decision making on non-detects, right? So I'm incorporating more into that question than they did ask. But in our sense, if it's less than 15%, I believe is our threshold, we'll just do half because that's been accepted by more regulators than not. If you are in a regulatory program, all these conversations happen with them on, do they want us to have a kind of a ramp approach to that data set? Do we want to assume all of it is the maximum, which some have, which I think is not very conservative? But we leave that part alone besides choosing half the detection limit. We only censor on the high end, right, as outliers, which is actually, again, the more conservative. I would truly want to censor from both sides in if I'm in a regulatory program and making these decisions. But that said, being conservative, we treat them as outliers only for the iterative effort of trying to see what happens when it is censored and does the data suddenly perform differently. And you'll be amazed at the performance elements. And so if you're willing to censor enough, like we'll have to arm wrestle in the office often on calling that an outlier or not. Because like I live in a state where there are formations that have arsenic upwards of 200 milligrams per kilogram plus, right? So it exists here. But for my data set for Texas, I'm chopping it. I'm sorry, you're out. I'll deal with those areas uniquely when I'm dealing with trying to develop a number that's not so for a large state, right? It's hard to develop for a state because I have subpopulations and I have to include them in some way.
Got it.
Did I answer a question in there at all?
I think so. It did for me. Kenneth, I have approval to go until like 2:05 if you're okay with that, because we do have some more questions.
Sure.
Great. Awesome. There was a question about interactions of multiple toxins with the idea that there could be synergistic effects compounding the toxicity. So are interactions of multiple toxins, are those included anywhere in those risk calculations or in the assessment?
Sure. So on the, if you'll remember, I had the scale with the like risk criteria and then background. Now, the side with the risk criteria, absolutely. Multiple contaminants needs to be weighed, and that's usually within different programs. So some programs consider additivity, whether there's 1, 2, or 3. Some programs begin additivity adjustments and weighting when there's 10 or more. So it just depends. Programmatically, your regulatory body will make some decisions of that. So the regional screening levels offer you some options in the modeling, and you can, play with those by getting not the default tables, but actually calculating your own specifically and putting your COCs in. But the talk today is exclusively on the background side, right? Just saying, I wonder if does this exist in a normal distribution or not? If so, what decisions can I make? Because I want the other side of that question. So there's no true additivity other than if we include arsenic in because it is a release, well, then it should be judged on. Now I pull it over on the risk side, right? Because it's a contaminant and it has a number because we have risk criteria for that. So that all happens there. But we first need to answer the question, was there a release? Does it exceed a background value? And so to that, I'd say we regulatory specific on the answer because you need to look like your program that you're going to close something in or address a release. But I need to answer the first question, which is, was there a release?
Got it. Great. And then going back, I guess, to some of those earlier slides, there is a question asking if you happen to know, or if you have more context for the EPA's decision to distinguish at less than half an acre or more than half an acre, because that changes your calculations, right?
Sure. So, well, you're pulling me over to my other side. I spend way more time on the risk calculation side, so that's fine with me. So the decision to use a dilution attenuation factor in that model has to do with the anticipated, truly the A in that word or that acronym, right? The attenuation. So knowing that something as in soil is going to leach, and so not a 100% mass can make it out of that model. We know it will be less than 1. And so the assumption of a acreage size gives you an indication of source strength. And so in all modeling, risk calculation, source strength plays a role in understanding. And so obviously I can't get back into the minds of what they were thinking in the early 90s when they calculated it for a bunch of different sizes, but most states look at that half acre because it came to them from EPA. And so all I can say is small source, we assume it's half acre or less. Large source, we assume that it has no attenuation. Let's be conservative. Even more important for you to actually get your background values then, right? Because in this case, the regional screening level had 13.5, rounded up to 14 for the table, versus 270. So I sat in between with these in the 20s. So that's why I needed the background in my cartoon scenario that I gave you there.
Got it. Got it. Another attendee asks, if you were updating a site-specific background, how would you go about that?
That gets very site-specific, right? So do I have a lot of different lithologies? Do I have a lot of different horizons that are unique, or am I going to group them together? Those decisions probably stem towards the type of release I'm investigating, but I'll say generally general truisms to mention probably is be in an unaffected area, collect enough samples so it is statistically significant. So the lowest number is 8, as you saw from our estimators. I probably would get up to the 20 if you can, because you get a lot of value being able to play with your potential outliers in there and understand it better. And then do exactly what we just did in the presentation.
Okay. Kenneth, this has been great. I'm going to ask one final question because there are actually a few that we didn't get to, but this one I think is a nice wrap up. Are there other resources that you would recommend to help understand this topic?
Sure. I'd say if you want to know really good background guidance documents, start with the Pro UCL website first, because the guidance document, there's a technical guidance document. Go to that. The second is go to ITRC. I'll give them a plug. Great people at ITRC, and they have a background threshold value document. So go there first, because then you're starting with current mindset, and then you'll work backwards. Or you could look at both of our papers, and there's tons of references in that too.
Excellent. Wow. That's where we're going to wrap up for today. I can see in the chat that this has been well appreciated. Thank you so much for sharing your expertise, Kenneth, and thank you to our attendees for those interesting questions. So yeah, that's all the time we've got for today. And anyone who's interested in reading more about environmental due diligence is encouraged to visit ERIS's info hub at erisinfo.com, where we have curated articles, podcasts, and past webinars. Again, I'll remind everyone that this webinar has been recorded and it will be posted on the ERIS website in the next few days. So on behalf of ERIS, my colleagues who've participated, and our audience, I would like to give a big thank you to Kenneth for sharing your wealth of knowledge and experience with us today. And again, to the audience, thank you for your attention and your questions. Please, everyone, enjoy the rest of your day.